Hello everybody, I'm back, and this is, I think, going to be the first part of kind of a longer video. This is going to be wiped down a few times throughout the course of this, because I'm going to try and go through Laplace's equation in cylindrical, in Cartesian, and in spherical coordinates, right? Now, why I'm going over this in particular is because of its utility that we see in upper level mathematics. Pardon me, I got some crud in my throat. Predominantly in applications like thermodynamics and, in this case, electromagnetism, right? So, what is Laplace's equation? Well, Laplace's equation is actually a pretty simple one. All it states is that sometimes you can have some function phi that satisfies the relation of the Laplacian operator, which is just basically your gradient squared, if you want to think of it that way, your del squared operator, is equal to 0. We typically use this in the realm of electromagnetism whenever we are dealing with a system that has some sort of applied potential on some sort of boundary, but there is not some sort of enclosed charge. If there was an enclosed charge, we would either resort to using something like Gauss's law, or more specifically Poisson's equation, which is identical to this, except it's equal to the negative charge density divided by the permittivity of free space epsilon naught. But anyway, with that out of the way, we've introduced essentially what Laplace's equation is. Now, depending on the coordinate system that you use in order to solve this partial differential equation, you need to be able to perform separation of variables within those different coordinate systems. A little redundant, I know, but anyway. All in all, I believe it was Hassani or Boas or Jackson. I need to review which one of these I'm actually referencing here in this particular case, but those are the three books I'm using for this particular video, and I'll link those in the description below and properly cite them. But anyway, I think it was Boas that wrote in hers book pertaining to Laplace's equation that a solution to a partial differential equation can be found in terms of an ordinary differential equation, and in order to do so, we just simply employ separation of variables. And in Cartesian coordinates, we just break up our one big function phi of x, y, and z into three separate functions of x, of y, and of z, right? So we have x of little x, y of little y, z of little y, instead of just x, y, and z of phi. Now what we do is we run that back through our Laplacian operator, and we get this ugly mess of functions and second partial derivatives being applied to these other functions. So we get yz times x double prime, xz times y double prime, xy times z double prime, all those summed up and set equal to 0. Now, because we're doing separation of variables, we want all of our functions to be paired with their appropriate partial derivatives, or derivatives for that matter, right? So in order to do so, we just divide this whole thing by x, y, z. And when we do that, we get this neat relation where we have the reciprocal of the function times its second derivative with respect to its sole parameter for each of those. We sum them up and we set that equal to 0. Now, in order for this particular formula to hold for some sort of arbitrary set of values, every single term in this particular equation has to be a constant. And we know this to be true, once again, because you can't have non-constants here and not have them sum up essentially to be 0 and still have some sort of satisfaction. So this can't be some sort of expanded function per se. This has to be equal to some number, some value that we have to assign to it. It can't be a function. I believe that might pertain to uniqueness theorem, and if I remember to put that in here sometime or somewhere along in the spiel, I'll include a little tidbit about uniqueness theorem and why that's important to solving differential equations of this kind. Anyways, what we can do is we can set two of these guys equal to these negative constants squared, and in order to cancel out these two, we set the third and final partial differential equal to another constant, which is just equal to the sum of those other two there. Now, if we allow alpha squared and beta squared to be greater than 0, then our solution to our Laplace's equation takes this form, where we have an exponential times an exponential times another exponential, where these two are imaginary and this one is real valued. Now, all this effectively does is let us cancel out those i's when we have the two in here and in here, but it possibly also pertains to, I would want to say probably somewhere the conformal mapping. I'm probably wrong with that, but the imaginary values, I believe, become a little bit more evident when we actually march down and solve an example of this. Once again, this is good. We have some sort of idea of what our function should look like in general, but we don't know what alpha is, and we don't know what beta is, we don't know what gamma is. We need to solve for what those values could possibly be, and in order to solve for what those constants might actually end up being, we need to be able to apply some sort of boundary conditions. I think it's probably because, I'll stand on this once again here. We have these I terms in here because of how these are set up. This will be some sort of sinusoidal, this will be some sort of sinusoidal solution, and this will be a hyperbolic solution. I know I'm correcting myself in the middle of the video, but I want to get things straight before I move on. It's also like 12 in the morning, and I'm very sleepy, and I'm not enunciating things like I should be, so I should probably not be recording at this hour, but this is just when I got around to it. Besides the point, that's where that comes from. Correcting myself in mid-video, that's fine. Boundary conditions. I'm just going to use this very classic example of boundary conditions being applied in order to get some sort of expression for our function phi, right? Namely our potential. So, move this out of the way because I'm going to need this later to finish up. We know, looking at this particular graph here, we have a cube, and it has side lengths of x equal a, y equals b, z is equal to c. And we only have an applied potential here at the top equal to v. All other sides are effectively grounded. They don't have anything being applied directly to them, right? So we can apply our boundary conditions for each of our coordinates. So let's just look at the x values first, right? So we have x equals 0 and x equals a. That's where our cube expands. So at x equals 0, we have phi of 0, yz is equal to x of 0, y of y, z of z is equal to 0. In order for that to be true, x of 0 has to be equal to 0 for all values of y and z. Similarly, we have the same case here, where instead of x equals 0, we have x equals a, and we do the separation of variables here, we set it equal to 0. Once again, the only way that that is possible is if phi of a is equal to 0, or I should have written x of a is equal to 0 more specifically for all values of y and z. So actually this should have been x of a. There we go. X of a for all values of y and z. So in order for this to be the case, we need to look at our differential equation itself, or more particularly just the x component of it, because that's the only value we're changing, and that's the only boundaries we're really concerning ourselves with at the moment. Excuse me. And what we see is that this takes the form of x double prime plus alpha squared times x is equal to 0. So when we think of functions that are, when they are derived, return the negative version of themselves, or a negative value of themselves, multiplied by some sort of constant, like alpha squared in this case, we usually think, oh, that has to be sinusoidal. That's our best guess for that. That's the standard guess for a differential equation of that form. If you've taken quantum mechanics before, I might have talked about it in one of my quantum mechanics videos way back when, but that's one of the solutions for a second order differential equation that takes that particular form. The Schrodinger equation, perfect example. This is just a rewritten form of the Schrodinger equation, if you want to look at it that way. Probably a hasty generalization, but it's the same kind. So we know that our function x should take some sort of exponential form like this, where you have big A, some constant, times an exponential of I alpha x plus b times e minus I alpha x. Or alternatively, we can use Euler's identity, sub some things back in, and rewrite it in terms of sinusoidal function, sine and cosine, right? That's usually a little bit more helpful for us because that's more directly evaluatable, if that's even a word. But in order to do so, we apply boundary conditions. We know we have that little x can be equal to 0 or a. So we plug in 0 for each of these. Sine of 0 is 0, cosine of 0 is 1. So we're left with b is equal to 0. So we know that that can go away. And then x equals a, that means we have a times sine of alpha times a, because we have alpha times x in our argument up here. We set that equal to 0. That means in order for this particular equation to be satisfied, the argument of our sine function here, alpha times a, has to be equal to n times pi for all integer values of n, simply put, right? So that has to be the case. And then once we know that this is the case, we have our value for alpha, which is what we've been looking for at the beginning. So in order to get the rest of our expression, we repeat this process. We do it again for the boundary conditions of y, and we do it again for the boundary conditions of z. And what we'll see is we'll get basically an identical result for beta, more specifically beta, not b. I should have been more specific there. We get the same result. It's once again another sine function. Whenever you apply the boundary conditions, the cosine term goes away. That second coefficient ends up being 0, and then the argument of that sine function also has to be equal to some sort of integer multiple of pi, and then we can shave off the other value that we don't need. I reiterate, we do the same thing for that. We get that beta has to be some sort of integer multiple of m instead of n divided by the distance b. And then when we do it again for z, we end up getting that gamma has to be equal to this expression here, where we have n squared divided by a squared plus m squared divided by b squared, all underneath the square root, for all integer values of n and m, because that was a prerequisite we had for beta and alpha anyway. And then we say then, because we have various integer multiples of pi that we can get, and various integer multiples of gamma and beta and n as a consequence, that phi actually has to be some sort of sum over these m and n values. So we have a linear combination of different states, essentially. That's one way you can look at it. We get some sort of mirroring that we would see in quantum mechanics, where we have a linear combination of possible states we can derive for our function phi, except instead of phi being a potential function, we would have psi being our wave function, and it being some sort of linear combination. Very, very subtle difference, same principle, right? So now that we have an expression for phi, all that's left for us to do is solve for a. Try not to show my face in here. Anyway, all that's left to do is solve for a, basically. And in order to solve for a, we have to apply something called Fourier's trick. And I, at the moment, do not have the board space, really, for that, to do a full-blown example of applying Fourier's trick here. I'm kind of skimming through my notes to see if I can find one. Nah, I don't think I'm seeing one. Also, it's just rather quite long, and you might usually see an application of Fourier's trick more frequently whenever we're dealing with spherical coordinates. But in other words, what we can do is that we can multiply these guys down here by orthogonal sine functions and integrate over the space we're dealing with. And when we do so, what we end up getting specifically, and also applying our overall boundary condition for the system itself at C, what we get instead, I'll erase this side here. This is why I grabbed this eraser earlier. Don't fret about me erasing things. This is a YouTube video. You can pause it. I'm not stopping you. Do as you please. I'll get some good space here, just so we can emphasize what we're doing. But once we apply Fourier's trick, and we multiply both sides by some sort of orthogonal sine function, and then also we also have to let our potential equal what our potential is at that particular boundary, at z equals c. What we end up seeing is that we could solve for our coefficients a, n, and m, which will end up being a, b, sine hyperbolic of gamma m n c over 1 like that, actually 4, sorry, times the integral from 0 to a dx, integral 0 to b dy, then our potential function bxy, and then times our sine functions here, so sine alpha n x sine beta m y, like that. And that's essentially all I can do with this particular example, unless I'm given some express value for whatever vxy is. So until I'm given that, and usually that's the case for a lot of these kinds of problems, is that that is given to you and then you can solve from there. A lot of problems will just say that, you know, a lot of them just say it's some constant potential, like so. But yeah, that's the Cartesian case in a very simple example, kind of halfway solved instead of totally solved. But with that, I believe now we can move on to spherical coordinates. So now that we've covered Cartesian coordinates, I believe now we can move on and start talking about some spherical coordinates instead. Now, the biggest difference between spherical coordinates and not cylindrical, Cartesian coordinates in this particular case is primarily the complexity in which the method of solving your separation of variables kind of just increments in its complexity, right? And increments is kind of a light word, I'll be honest. It kind of explodes in complexity, because instead of dealing with just your simple standard boundary conditions like you do in the Cartesian case, where everything's nice and square, things get a little bit funky when you're dealing in terms of things of your azimuthal and your polar and your radial components, right? As you can so very much clearly see. I'm going to try and get up off my bed so that my desk doesn't flip. Instead of just having, you know, our partial of our phi function plus another partial of our phi function plus another partial of our phi function, we instead get this mangled wreck of an application of the Laplacian and spherical coordinates. Usually you can look this up in the back of your textbook. It might have this or the Laplacian operator given explicitly in your textbook. Some textbooks, if there's an appendix and they're decent enough to supply you with one, they might actually also have a derivation of that particular operator in the back of the book. I know Griffiths does, although I don't really recommend Griffiths for this level of work, because Griffiths likes to work in non-cylindrical cases. He's not a fan of the cylindrical case, and you need to know cylindrical coordinates in order to do E and M effectively and properly, because what are wires if not very small cylinders? Anyway, textbook complaining aside, we have to apply separation of variables, and we get our function in terms of our polar angle theta, our function in terms of our azimuthal angle phi, and then of course our function in terms of our radial distance r divided by r, which we usually see in the case for like a potential of a point charge, right? You have some generalized function with 1 over r dependence. I believe that's where that comes from in this particular case. If you want to get into the more intricate math, this r 1 over r term that propagates throughout here probably comes from the Jacobian whenever you're doing some sort of change in variables. But this is a physics class and not a math methods class, so if you want to see that, there's probably some videos out there somewhere, and I can find them. I'll link them in the video below as well, so you guys can see that. Or heck, if y'all want to, I can even do that derivation for another video if you guys want. Anyway, we set this equal to 0, and we substitute this value of phi back into our Laplacian in spherical coordinates. And when we do that, we basically apply the same trick. We divide by a certain amount here, namely the PQU term, right? And then I think an r squared over sine theta term as well to get that out of the denominator. Specifically, I believe Jackson says that we divide by a factor of, it was, r sine squared times r squared divided by UPQ. Yeah. Then we'll get this particular expression here, which is already nicely and cleanly divided up into U dependencies, P dependencies, and Q dependencies. The easiest one to look at is the Q dependency, because we just have a second derivative of Q with respect to phi times 1 over Q, and we can apply the same logic as we did in the Cartesian case, and we set that equal to some constant negative m squared, where m is positive, and that means that Q will have solutions of plus or minus im phi, right? It gets a little bit more tricky when we look at P and U, our functions of theta and phi. P in particular is a bit of a booger, and we're going to actually have to bust in some Legendre polynomials to discuss how to solve those, or to properly assess them in our problems in this derivation. And then our U term is a little bit less ugly when we look at it. So we'll look at this one first. Also, just as a side note, this L times L plus 1 term, L is also an integer. These come from the spherical harmonics, I believe, and we'll see how they come into play. They don't come from the spherical harmonics, they come from the Legendre polynomials and the associated Legendre polynomials, which then show up in the spherical harmonics later on down the road. So, if we look at just U, Jackson makes the comment that it's apparent that a single power of R, rather than a power series, will satisfy the function U. So what he does is that he writes that U is equal to some constant of A times R to the power of L plus 1. And I say this because it's kind of itty-bitty, don't know how well you guys can see it, plus B divided by a factor of R to the power of L. Once again, L is just some integer. For P theta, once again, it's ugly. Legendre found a neat little trick for solving problems that look like this, and namely in the standard form we would let x equal cosine of theta, and then we plug things back in, and then we can get p as a function of x instead of p as a function of theta, or namely cosine of theta, and we get that the derivative of 1 minus x squared, which kind of parallels, where did it go? Crummy, somewhere over here. This tidbit over here. Times the first derivative of p with respect to x plus L times L plus 1 minus m squared divided by the quantity 1 minus x squared times p is equal to 0. The solutions to this particular function, or not function, equation, are the associated Legendre polynomials, which are a slightly different set of polynomials themselves. And the solution by power series is what Jackson wants to look at in particular to prove this. So what he does is that he takes the above expression, he looks at the case where we have azimuthal symmetry in our spherical system. So if we're to draw some sphere in our little coordinate plane here, right? Here's our sphere, like that, right? Azimuthal symmetry just means that we have the same we'll get the same value for phi, or big phi, all the way around our sphere there. So it doesn't matter which way you turn phi, the value of our function is not going to change. However, it might change though, it doesn't negate, we might see a change in theta if we move theta, and we might change if we see some change in r. And we'll definitely expect to see some change if we move it with respect to r, because we have that 1 over r dependency. Anyway, what Jackson does, and I really didn't fill in too many of the gaps here, but he sets our function p of x equal to a power series of x to the power of alpha times the infinite sum from j equals 0 to infinity, redundant, of a sub j times x to the power of j, and he throws that into the associated Legendre polynomial. And as a consequence, we get a new series once we take the derivatives, and a particular recursion relation that will take a form that I will write out in the next slide. Okay, so our resultant series takes a particular form, being this infinite sum of this nice long string of terms, right? So we sum over alpha plus j times alpha plus j minus 1 times a sub j times x to the power of j plus alpha minus 2, because we take a derivative in the previous term, right? And then we subtract from that the product of a plus j and a plus j minus 1 minus our L times L plus 1 term, all multiplied against a sub j times x to the power of j plus a. And then all of that gets set equal to 0, because we're once again trying to solve the Laplacian for this thing, right? So when we begin to plug in a few first couple of terms for j in our series, right, namely for j equals 0 and j equals 1, what we notice is that we get two different results essentially. Namely that we get a naught isn't 0 when the product of alpha and alpha minus 1 is equal to 0, and we also get that for alpha, or a sub 1 isn't equal to 0 whenever we have the product of alpha and alpha plus 1 not equaling 0. If we look at either of these cases, we can actually derive this following recursion relation of a sub j plus 2, where it's equal to, and I don't know how well you guys can see this, so that's why I'm pointing up here, of alpha plus j times alpha plus j minus 1 minus L times L plus 1 divided by the product between a plus j plus 1 and a plus j plus 2, all multiplied times the ajth component. Those are your coefficients, right? And after some short inspection, we basically see that whenever we plug in values of j that are succeeding, or even 0 and 1, we get the same recursion relation. So what we can do is that we can pick either of these two conditions to begin with. Not both, but either one of them. Because if they're both, then the sum doesn't sum right, simply put. We'll be summing over terms that we are forcing there not to be, and then that screws up our result, right? And imagine just taking a whole number out of like the Fibonacci sequence, right? Then it doesn't work. Or not the Fibonacci sequence, some power series, some Taylor expansion. Then you don't get something that's exactly equal to the original expression you're trying to sum out, right? So Jackson goes on and decides to choose the prior case with a naught not equaling to 0. So if that's the case, then for the power series, we can only have even powers of x whenever alpha is equal to 0, essentially, or only odd powers of x, or whenever alpha is equal to 1, in either of those cases. We can also see, upon further inspection, some particular characteristics of this polynomial, namely being that it diverges at x is equal to plus or minus 1, or it terminates otherwise, namely for when L is equal to 0 or when L is some sort of positive integer. Basically that causes a sub j plus 2 to terminate whenever L is equal to one of those quantities. And then the surviving terms, one or the other cases whenever L is some even integer, the alpha equals 0 survives, or whenever L is an odd integer, the alpha equal 1 term survives. We can actually begin to create our Legendre polynomials from this sum, right? So L equals 1, 2, 3, 4, and 5, and 6. So we get these odd terms surviving and these even terms surviving with each iteration of L over the sum. Your textbooks will have those. Jackson has them in here as well. I didn't write them out because I thought I was going to run out of board space before finishing this particular subsection and moving on to an example. And Jackson really gets into the weeds into this portion of the book. And because it's about 1:40 in the morning right now, and I don't believe I have the brain power to copy down things in a book and properly explain them to you, I set up the initial condition to express the orthogonality condition of the Legendre polynomials. And then we get, after a bunch of different steps, we can actually describe an orthogonality condition with p prime of L being a different Legendre polynomial, namely where L prime and L are different values, right? Anyway, I completely just glossed over the fact that you can also generate some of your first Legendre polynomials, if not all of them, rather meticulously, using Rodriguez's formula. Rodriguez's formula isn't necessarily a generating function. I don't want to use that term too loosely, because that kind of refers to some other things as well. You can have your Legendre your standard Legendre generating. That is a hard sentence to say at 1:30 in the morning. You have Legendre generating function, which is like 1 over the square root of some radial mumbo jumbo times an infinite sum over of r greater and r less than times the Legendre polynomial PL cosine theta. Long story short, that's another video in and of itself. That's covered in Hassani. I do know if you guys want to see me talk more about Legendre polynomials in more detail, I will gladly do so. But as it stands right now, I more or less just wanted to introduce you guys to the concept of Legendre polynomials so that you guys know what the heck they're doing in our formulations, right? But yeah. Now that we're generally familiar with the fact that these things are around, they exist, and there's lists of them in your textbooks that you could probably refer to get the first couple of ones, we can actually begin to apply our Laplacian for spherical coordinates within some sort of azimuthal symmetry. So like for a sphere, for example, right? Okay, so if we're looking at, let's say, a problem where we have azimuthal symmetry, what we're going to point out immediately is the fact that we just don't really care about phi. So we're going to write our function for a potential phi as just being in coordinates of r and theta, right? You know, we make an emphasis of the fact that our constant m has to be equal to 0 in the cases whenever we have azimuthal symmetry. And this is important because we are going to have cases later on discussed whenever we have m not equal to 0, right? So down here, but we'll get onto that. I'll expand this up here. I'm writing kind of over there because I was just scribbling on it, so it's the last thing that was really on my mind. Right. So whenever we have that, we employ our separation of variables, yada yada yada, and we get that our value phi should be some sort of superpositioning of our radial function and our theta function, which is just this infinite sum over L equal to 0 of a sub L times r to the power of L times, not times, plus b sub L divided by r L plus 1 times a Legendre formula, or a Legendre equations where the argument is cosine of theta, is representative of our theta dependency of the potential itself. So, which is neat because now we have these nice clean solutions that we can just kind of plug numbers into and get whenever we are evaluating our problems. Later on down the line, that is. But anyway, so let's say somewhere along the surface of our sphere, our potential phi can be just described as being some potential v of theta, right? And we want to know what the potential is inside of our sphere, right? So if we're looking at the potential of inside of our sphere, what we're going to do is that we're going to begin to apply our boundary conditions, right? So when we apply our boundary conditions, we need to think of where is this particular function actually physically possible. So let's say we take our radial component, right? We take our radial component and we reduce it all the way down to the origin, right? We want to say what's the potential at the origin, or whenever r is equal to 0. Well, when r is equal to 0 here, then we know that this term can be equal to 0 because r would be equal to 0. The issue, though, is that we have a coefficient over r. And if you know anything about fractions, which I hope you do if you're watching this video, as some denominator gets smaller and smaller and smaller, or we take that variable of 1 over r to a limit to infinity, or actually, sorry, to a limit to 0 in this case, then our term blows up to infinity. And we can't have an infinity just sitting inside of our sum. So in order to nix this physical impossibility, this coefficient b of L has to be equal to 0 for all values of L. So we just get rid of that term completely. We get rid of the 1 over r dependence here in our sum, because it's just not physical. So in order to get our a sub L terms, and it looks like a little bit like a delta here, but fix that. There we go. And it looks a bit like a delta. I just needed to correct that there. Right? We apply our boundary condition on the surface of the sphere itself. So we set the remaining portion of our sum equal to the potential v of theta, and then we apply Fourier's trick. And once again, Fourier's trick, you take those orthogonal functions of the Legendre polynomials, you integrate on both sides, and then you can isolate a at that point. And namely, in this case, when you do that, we get a sub L is equal to 2 times L plus 1 divided by a to the power of L, where a is the radius of our sphere, multiplied by the integral of our potential v of theta times our Legendre polynomials, or our theta-dependent portion of the function whenever we were getting our separation of variables sine of theta d theta. Now, when we do this, my goodness, my arm's itching like you wouldn't believe right now. But we can't really do anything more with this until we know what v theta is numerically. And until we know what the heck that is, we can't really do anything with it. That's kind of redundant. So let's actually do something with it. There's an example in chapter 2 of Jackson wherever you have a sphere that has a slight discontinuity around the equator. So you don't have any potential there, but you essentially just have two different half spheres or shells that are in contact with another, basically, for lack of a better word. So they have an infinitesimally small insulator, infinitesimally small perfect insulator between the two of them, such that they constitute two separate, equally sized hemispheres. And we want to know what the potential is inside of this particular getup. Well, now we can assign values to our v of theta. So in this case, we assign a positive potential v for theta values that are between 0 and pi halves, so anything kind of doing one of these, right? And then we assign a negative potential to any one of them between pi, which sits at the bottom here, towards the equator at pi halves again, right? In that case, we can state that our potential at the radius r, or at the radius a, becomes a sub L times a to the power of L multiplied by the Legendre polynomial p sub L cosine of theta. Now, earlier on in the chapter, whenever Jackson was going through and deriving the orthogonality conditions of these particular functions, what he noted was that you can actually expand our polynomial in Legendre, or any general Legendre expansion, right? I believe, if I want to be very specific here, when I call things what they are, he said that this was the general series for the Legendre polynomial. My apologies. The general series for the Legendre polynomial can be written as the sum of L equals 0 to infinity of a times L p sub L of x multiplied out. So we get our odd and even terms with positive and negative signs. What's the word? Not zigzagging, but they iterate between positive and negative values for the Legendre polynomials. And the Legendre polynomials, the only ones that are surviving are the odd terms, and I think that comes back to the a naught does not equal 0 case, or does, there would be the a naught equals 0, I think. You can review that. My brain's not remembering about 20 minutes ago. Besides the point, what we end up getting is this other expression that ends up mirroring what we get for the general series for a Legendre polynomial, but instead of having x as our argument in the Legendre polynomial, we have cosine of theta, and then we have this sneaky little r over a term. Now we're picking basically some value of r inside of the sphere which has a radius a, so it would only constitute a portion of that total radius. So that's why we replace the a to the power of L with r divided by a to the power of L. So with that in mind, you can approximate it, and I just wrote it up to the first three terms because I wasn't thinking to leave room to write ellipses on my board. and it looks something along like that, and you can factor out the value for v for each of those. Generally, some other comments about spherical coordinates or spherical Laplacian equations is that along the axis of symmetry, what we see is that we can just write our potential as just being a sum over the radial components of our potential itself. And then in the case where it gets really crazy, we have phi is equal to a double sum times this YLM figure here. If you're not familiar with this YLM figure here, this is our spherical harmonic, or rather, our spherical harmonics. These come from the Legendre polynomials. There's a rather tedious and mathematically rigorous proof to show where these come from in Jackson. We can derive these in another video if you guys want to. I might derive them in my quantum mechanics thing that I'll be working on later on in the year for review as well. But for now, just hold on to the fact that those exist. And the general Legendre, the general spherical harmonic can be written as the square root of 2 times the number L plus 1 divided by 4 pi multiplied by L minus m factorial divided by L plus m factorial times the associated Legendre polynomial of cosine of theta times e, that doesn't look like an e, it looks like a plus sign, a really pitiful little plus sign, e, I am phi, my bad. And our associated Legendre polynomial itself is a whole other expression being negative 1 to the power of m times the quantity of 1 minus x squared to the power of m halves times the L plus mth derivative of x squared minus 1 to the power of L. Now, that's a gosh darn mouthful. For this particular series solution, we have variables a sub L of m and b sub L of m. Once again, we can apply Fourier's trick in this case still. That still holds because we're dealing with Legendre polynomials and their orthogonal set of functions. And because they're orthogonal, we can abuse that and multiply both sides by some orthogonal version of itself. Terms will cancel. We can integrate. And usually for a really general case, digging through my notes and namely looking at problem, I believe it was, where are you? I believe it was problem 3.4, or no, 3.3 in the first edition of Jackson, that we can derive this general expression for a sub L of m being a to the power of negative L times the integral of, this needs to be the omega, my bad, the omega times the potential V times our complex conjugate of our spherical harmonic. Sine of theta, d of omega here is just d phi, d theta here. If you don't know what a complex conjugate is, essentially it just means that you change the sign on any sort of complex variable that shows up in our spherical harmonic. So for instance, the complex conjugate of our L of m here would be identical, save the fact that this exponential term would have a negative Im phi in the exponent. Last but not least, if you notice something about the sum, we have one sum which just starts from L equals 0 to infinity, and the second sum starts from m is equal to negative L. That is because of how these particular subscripts are related to one another. M can take on all values of L. So if L is equal to 1, I'm sorry, I need to word this more specifically. M can take on all values of plus or minus L. So we have to sum first from negative L all the way to positive L. So if, for instance, L is equal to 2, then M can assume values of negative 2, negative 1, 0, 1, and positive 2. And then we can iterate through that, plug them into that while M there, and actually calculate our values for that while M. For those particular values of M and L. And that's how you would do this in spherical coordinates. I'm going to make right here specifically a transition very briefly to an animated tidbit because I took a photo of the setup of the Bessel function in the cylindrical case. More specifically, you have to use Bessel functions in the cylindrical case, and I took a photo of that, and I didn't feel like recording that day, but I made sure to take a photo of it so when I did get to recording, I could actually just plug it in and deal with it there later on. And moreover, it was going to be completely out of order. I would have started in cylindrical coordinates, but I wanted to work on something that was familiar to everybody, being the Cartesian case, and then move on to the cylindrical component. I don't think I'm going to show any primary examples in the cylindrical case because it's really the same procedure. You just have different coordinates and you're applying different boundaries to it. I might take that back and do like one, but I'll see how I'm feeling here in a little bit once I actually record, put things together, so on and so forth. And yeah, on to cylindrical. So in this portion here, I wanted to discuss the Laplace equation in cylindrical coordinates. So essentially what we do is that we perform the same standard procedure of taking our function phi, we split it up into different other functions of rho, our radial distance, our azimuthal angle phi, and our height z, right? We do our separation of variables, we solve our second order differential equations, but in particular this one takes on Bessel functions. And because we have Bessel functions, we have to concern ourselves with how they look and what forms they take. Primarily, we will refer to our Bessel functions as our J sub nu terms over on the right-hand side. And we can even show that these particular Bessel functions exhibit some amount of orthogonality, right? So once we have these Bessel functions in mind and we have our initial conditions of our system, we compare these things together and begin to solve for rather complex applications of our Laplacian in this coordinate system. Now, I did find one pretty darn simple example in another textbook. NIFA wrote, I don't remember what year the copyright is, but I also did work it out a little bit on the board back at where I work because I was bored and I needed to practice because I thought I had a quiz coming up pretty soon. So I did that there. And that particular question will be seen right about here. I also wanted to point out that we can find that orthogonality condition. Don't remember if I just said that or not. We can find that orthogonality condition by multiplying both sides by some orthogonal function or some orthogonal Bessel function because they constitute that same sort of basis set that we've been discussing in previous instances, namely the iteration in the spherical coordinate case. And then what we get is that we get a relationship with delta, and then once we apply Fourier's trick again once more, we can express our coefficients a sub nu of n as well in terms of our function, f of rho, or some radial function, times rho being our radial distance, times our Bessel function j nu with an argument of x sub n m rho divided by a, all over that radial component. So that's pretty nice. Pardon me, a little bit tired. It's about 3 in the morning. But yeah, with that in mind, we can solve Bessel functions, and we can solve for our coefficients, and at this point we just need to know what our potential is, f of rho, in order to continue solving this kind of problem. Here I've chosen a pretty simple example that doesn't have to deal with the Bessel functions. In this example, which is pulled from NIFA's Introduction to Electricity and Magnetism, we have a rod. It has z-symmetry and azimuthal symmetry, so all we have to do is worry about the rho component, and when we have the rho component, all we need to do is worry about separation of variables. And we want to first actually derive some expression for phi before we go into separation of variables. So in order to do that, we have to integrate quite a bit. And when we do this particular integration, we have to use our integration by parts method. And when we do that, we derive the fact that our potential should be equal to some constant over p, basically, or over rho, my apologies. The first derivative of phi should be equal to c over negative p. And then we continue with this particular integration, right? And when we continue doing this integration, we get that our potential is actually a natural logarithm from rho naught divided by rho, where rho naught is some starting position away from the rod, and rho is the actual position of our viewing point. We can relate that to our surface charge sigma, right, using the definition of a surface charge as it pertains to a potential, and then we can solve for c that way and just plug it back in, which is exactly what we do. Now NIFA goes the extra mile and just slaps the fact that we can get a scalar value for the line charge of our line, but it's okay if you just leave it in terms of the surface charge. You can get the line charge from Gauss's law, but it doesn't change the fact that you have that natural logarithm relationship in there. All in all, you should get phi times some constant times a natural logarithm term.